Welcome back, Precalcsters. For today, I am hopeful that you have all brought with you your wonderful aprons because today we cook. Specifically, yep, I'll wait for applause and laughter to end. All right, now we're good. So, today we are jumping into what I would still also consider one of my favorite topics, and pretty much all of Trig, it turns out, is kind of my favorite, one of my favorites. But we're looking at 5.3 today. And in 5.3, we're going to take a step forward. We've looked at simplifying, we have looked at how to verify identities and make sure that the things that we're writing really are true. In fact, the purest version of truth that you will likely encounter, definitely today. And we're going to go a step further and start connecting this back to algebra. And specifically, we're going to be applying all the things that we've seen thus far, and we're going to begin solving trig equations. Now, in here, there are a lot of easy techniques that we've seen, and there are some couple little strange ideas that we have to account for. Now, the first thing that I want to specify is if we think about a basic equation. So I'm going to call this little first section, we're just going to build a little bit of intuition and see that, hey, we can make sense of where these go. If we consider the graph of something like sine, and I'll graph a really rough sine function here without putting values on it. So let's see, I know that sine starts at an angle of 0, and I'll switch colors so it's a little bit easier to identify. But sine starts up and then it goes down like this. So this is a sine wave, and it's roughly sketched, but it's a sine wave nonetheless. Now, if we have an expression or a graph like this, a function, and I want to know for what angles or what variable in this situation does it equal a specific value, and that's getting weird, we can solve it. And just to make sense and really clarify what it is I was getting at, if we consider this graph, the sine of x, and I asked us to solve when is it true that sine of x or theta or t, it doesn't matter, for which angle does the sine of x equal 1/2? There's a few different viewpoints that we can take, but we are going to specify like crazy as we're doing this. Now, right off the bat, if this is 1, I see that, hey, it looks like there's a 1/2 there at this x value, and there's a 1/2 there at this x value, and a negative down here, and a negative down here, and another positive right here, and a positive right here. We wind up seeing that we can have infinitely many solutions because this sine function waves forever. So we're going to think about this and just make two little comments. If no interval is specified, if there is no interval specified, we have infinitely many solutions. Now, rather than just stopping here and saying, hey, cool, we have infinitely many solutions, what we're going to do is we're going to think this out. And you may want to have a unit circle out, but if I look at the unit circle, and these are just two different ways to view the same function, right? Because we can graph it as we go past a circle, or we can, graph it on the circle. When I'm looking for where is sine of x equal to 1/2, I see there's only two places where sine of x is positive 1/2. And specifically, it happens at the angle, or x in this case. It happens when x is equal to pi sixths. And it happens when x is equal to 5 pi sixths. So this is just that first little circle. Now, here's the deal, though. If I take this angle and say, check it out, here it is, I've gone to pi sixths. I could go another full circle and wind up at the same y value. Or if we want to view it here, if here's my first, I'll switch colors again. If this is the first pi sixth, then all I have to do is go one full period over along my function, and it looks like it's right here. There's one period. And check it out, here's another 1/2. That's just 2 pi over. And if I go another 2 pi, I'll get another one right here, and so forth and so on. And the exact same thing happens here. It's a positive 1/2 at 5 pi 6. So here I am, and I go another whole circle, or add 2 pi to this, and I wind up right here. So I can take, from any solution that we find, we just take the next period over, and we're going to get the same answer, which means there's a nice way to write this. And it takes a little bit of practice, and we're going to be really formal for here, or for this, but let's take a look. For this equation, I know that sine of x is equal to 1/2 at 2 places. So we'll say that this is, first, it happens at pi 6, but it also happens at any full period away from this. And it doesn't matter if we go 1 full circle, which is 2 pi radians, or 2 full circles, 4 pi radians, it's always going to wind up there. So the way that we indicate this, and I'm going to annotate and write a little bit more, instead of just saying 2 pi, we're going to let n be any number, as long as it's an integer, and just say, hey, 2n pi is just n circles. So if n is 1, we go 2 pi radians. If n is 5, we would go 10 pi radians, which is just 5 full circles. Where only thing that I'm going to indicate here is, and we won't have to do this normally, we'll just work with the assumption, but I'm going to say that n is an integer. So as long as n is a whole number, an integer, whether it's positive or negative, doesn't even matter, we're going to go a full period. Now, this wasn't the only solution. That hit this one, and this one, and this one, and I suppose there'd be another one over here that I can't see. So I'm going to specify, and this solution is also satisfied when I go to 5 pi 6, and I go any number n of circles or periods away. So same expression, plus 2n pi, but notice we started at 5 pi 6 plus 2n pi, and 5 pi 6. We have infinitely many solutions expressed right here. Now, when we're dealing with these, and we'll see this a little bit later, I'm just going to front load it a bit. Oftentimes, we'll specify that, hey, I just want to work on 0 to 2 pi. And it's starting at 0 and ending at 2 pi. And we'll talk about the open and closedness of that set. But if it's not specified, your answers must include this. So that feels important enough because it took 3 musts. If no interval specified, weird emphasis there. If we don't have an interval specified, we need infinitely many solutions. Now, for our situations, whoa, I was going to say infinitely many points and solutions at the same time, and I tried to say pollutions. Solutions. Now, when we're looking at this, I don't want to just generalize and say, oh, it's always plus 2n pi, because maybe things get wonky, but this covers it. Cool. So we have a little bit of intuition for how these things start to work, and realistically, we just started solving them. So what I'm going to do is a little bit of editing magic, and it's going to require that somebody in class pauses and resumes here in a second. But with the snap of a finger, we have the problems. So for this, we are going to be collecting like terms. You do not have to write this, but it's just solve it like it's regular and just deal with the sine and cosine as needed. But I want you guys to get example A written down in your notes, and we don't need somebody to pause it here necessarily, but I want to work example A as not with you because you're not here. I'm going to work example A and talk through it, and then I want you guys to try example B. So I'm going to go fairly quick on these, and as always, super duper important that not only are you like writing stuff down, but I care more that you're understanding. So while I want you to have this in your notes, ultimately, I would rather that you at least absorb and really acknowledge and think about the things that I'm talking about as we go through, and then apply these ideas in your notes when you're working with your neighbors here in a moment. So this first problem, sine x minus root 2 equals negative sine x. If we wanted to think about the graph, I know that we could graph it. And I'm not interested in drawing the graph and trying to estimate where all these solutions exist. There's going to be infinitely many of them. but let's take a look. So right off the bat, if we're just collecting like terms, just like we do in algebra, anything that has an x in it, or a variable generally, but an x in this case, I'm going to get on one side. So I'm going to add a sine x to each side. So we get 2 sine x minus the square root of 2 is equal to 0. And then I'm going to do 2 steps in one now because I just want to isolate the variable. And it's stuck inside of my sine. That's okay. I can deal with it. I'm going to add a root 2 and then divide by 2 so that I ultimately wind up with sine x is exactly equal to root 2 over 2. Now, this is a value that I recognize because this shows up on the unit circle. And this is the strangest idea that we encounter with this, but I want to talk it out here, and then I would encourage you guys talk this out as well as you're thinking about it and seeing if it can make sense. Because there's a lot of ways you can write this answer. So if you check your unit circle, I see that there are 2 places on the unit circle where sine of x is root 2 over 2. Now, I might have had a different example in my mind as I was thinking about this, but I noticed that those places are initially pi fourths, because we have positive root 2 over 2, and then any full circle after that, which is just 2n pi away, and there's another place where it happens, because it also happens at 3 pi fourths in quadrant 2, where we have a positive sign again, but I can go any full circle after the fact as well, and we wind up here. So once we get here, it's just a matter of, do you really have the unit circle down? And if you do, awesome. If you don't, less awesome, but you do have a unit circle which you can use to make sense of this. Cool. So what I would like you to do is, if there's anybody in class who has issues, doesn't understand something we talked about, and on the flip side, there's somebody that does understand, I want you guys to use that time now to discuss this. I'm not there to answer your questions, but I have full confidence that somebody in class is comfortable enough to explain this to your peers. Cool. If you're discussing, awesome. If not, it'd be cool if you did, if you need to. But I want whoever's running the pictures today, or the screen rather, I want you to pause it now, and you will see in just a moment my detailed solution for this one. You are replicating this process. So pause as soon as you can, and you're going to see this solution detailed in 3, 2, 1, and here it is. So I took smaller steps, or larger steps this time rather. Cool. The common mistake that somebody might have is double check, because anticipated that somebody probably has 5 pi 6. And if you do, I like where your head's at, but you need to be real careful about the sign, whether it's positive or negative. Cool. So speaking of that positive or negative idea, we get another type of example where I don't love the name of this one, but I get why it's called this. Another type of problem that we're going to see requires us to extract roots. And that is really fancy language, but when we talk about extracting a root, all that it means is we need to take a square root of something. And so long as we are careful and we remember what needs to happen when we take a square root of an equation, both sides that is, we should be able to cover all of our answers. And this is the weird idea with the solutions that I was getting at on the previous example. I just had it mixed up in my head. So for our first example with extracting roots, what we wind up getting, and I'm just going to do one example of each and then ask that you guys do it just like we did the previous one. So for our first example, let's say we're working with something like the following. We get 4 sine squared this time, 4 sine squared x minus 3, and I'm trying to find the roots of this function, or the zeros, the solutions, however you want to think about it. We are solving this equation. Now, right off the bat, I'm going to do 2 things. Yeah, good point. Great call there, Sean. I'm going to add 3 and divide by 4 in one line. Good choice. So here we go. Getting this, just like we do with all algebra, I'm going to isolate just the thing with the variable. So I'm going to add a 3 to each side, and then I will divide by 4 so that I'm left with only this. Now, we are trying to solve for x ultimately, but it's unfortunately stuck within a square. So the good news is we have a way to deal with that. I'm going to take the square root of the left to get sine x. And I'm going to take the square root of the right. And I'll write it out here just so we can. This becomes the square root of 3/4. And it's been a while since we've been in like algebra land. So I'm going to do this in a couple steps. And if anybody notices a mistake that I have made, intentional or not, I want you to spit it out because there's some issue with this and when we take square roots. So I'm going to keep making the mistake. Feel free to shout it out loudly and proudly if we see it. But I'm going to keep splitting this guy up and then I'll fix whatever my mistake was. So here I know that the square root of a fraction is just the square root of the numerator over the square root of the denominator. This is the quotient property for powers is what we wind up seeing. And we're just taking little steps, but I think I wind up with the square root of 3 over 2. Okay. If you haven't noticed the mistake yet, I want you to pause where you're at, like not literally on the screen, but I want you to take your eyes and put them in the direction of the screen. Whenever we take a square root, I have to account for both the principal and the negative version of it. So the square root of 25 is 5, but it's also negative 5, which means huge mistake that's going to leave half my answers missing. When we take the square root of a number, we add our plus or minus every single time. Now, notice what happens. We have sine of x, and we're looking for where is it root 3 over 2. And if you want to think about taking the arc sine of stuff, you can. But because this is a value that shows up on our unit circle, it's worthwhile just to use our unit circle rather than thinking through all the trig stuff. So let's see. I'm looking at this and I'm thinking, okay, where is sine of x equal to positive root 3 over 2? And what I recognize is this happens at 2 places. It happens for the first time at pi thirds plus 2n pi. So any full circle. And I'm going to change the way I've been writing this. It also happens at 2 pi thirds. So quadrants 1 and quadrant 2, sine is positive root 3 over 2. So it also happens at 2 pi thirds plus any full circle after that. Okay. We have 2 answers at this point. These are both the positive version. Now down here we also have the negative. So if I'm looking and I'm thinking about my unit circle, and again, I would encourage have your unit circle out, let's verify it. I think that the first place that this sign is ever negative root 3 over 2 is going to be, and I got to think this out, 4 pi thirds. Plus any subsequent full circle. And it's going to happen one more time at 5 pi thirds. Plus any full circle. Now, this answer is completely fine. This is good. If you want to stop here for your solutions, I'm fine with that. But as you all, I imagine, know by this point, anytime that I get a chance to write less, I'm going to seize it. And what I want us to do, just to think about this, is if we look at our unit circle, and I'm not going to draw a perfect circle, or I am, and it's going to be way better than normal. Okay, if we think about what's just happened, I've identified these points on my unit circle. And as you get more comfortable with the unit circle, this is going to feel more natural. But what you'll notice is that each of these, so pi thirds and 4 pi thirds, these ones link together, it seems. They're exactly pi radians apart, or a half circle if you would rather. And then 2 pi thirds and 5 pi thirds are exactly pi radians or a half circle apart as well. Now, the reason that I'm even bringing this up is we have an alternative way to write our answer which is much more concise and kind of to the point. So this answer is good, and it's full credit. I'm fine with it, but we do have an alternative. Instead of writing all four of them, I'm going to put a big or here to say, hey, look, here's one way to write the answer, or we can write it like this. Instead of writing all four, I think that I could just start at pi thirds, and then from this point, I just need to go a half a circle. And then another half circle would get me to another one, and so forth and so on. And instead of having to worry about adding 2 pi on each of these, we could just start here and simply add any number of half circle. So whether it's 1 or 2 or 3, doesn't matter. Any n half circle away is going to be okay. Now, similarly, with this other piece, 2 pi thirds and 5 pi thirds were exactly pi radians, or half a circle apart, which means we could express this solution, these two, as a single expression as well here. And if our first answer is good, and I'll take it, this one I would consider is great. This answer is more concise, it's more clear, easier to write out. Now, you may gravitate toward this first one, the good option, and that's completely fine, but there is value and utility in doing the great option. So what I want you guys to do is, working with one another, I want you to do one more problem, and you can write your good answer, that's fine with me, but with your neighbors, I also want you guys to reach the great answer, the most simple way that we can write this. So for example B, you guys get the problem, the privilege of solving the problem 2 cos squared x minus 1, and I want to know when is that equal to 0. Okay, whoever is running the show, go ahead, pause this, and you will see my detailed solution without further discussion in 3, 2, 1, and here's my detailed solution, sort of. So I included a set of ellipses in here to show me skipping some steps. And Alex, if you were in class, I want you to go ahead and answer this. Why or how did this become square root 1/2? Why did it turn into root 2 over 2? Louder. All right, yeah. I assume I'm cool with that answer. I hope so. If not, just to make sure that I heard it correctly, Fern said that, hey, we get 1 over the square root of 2, and then we rationalize by multiplying by root 2 over root 2, and we obtain this. Okay, for this problem, this is that great answer that we talked about. Now, we could probably go a step further, though, and we could get the greatest solution out of this one. And you can't always do this, but I want to make sure we can see it. On our unit circle, these are the places that this just happened. Cool. So if we're here, we're trying to solve this thing. I recognize that that's a half circle and that's a half circle, hence the n pi's. However, if we wanted to look at just going from pi fourths to 3 pi fourths, we have simply added a quarter of a circle, or if you will, a pi halves, which means since we've only had to go a pi halves here, and then we went another pi halves from here to here, and another pi halves from, I don't need to change colors, but I'm already committed, here to here, and so forth and so on, then maybe, just maybe, we can write this as the greatest answer if we see it. So rather than writing it here, we could just start at pi fourths and add any number of quarter circles, or n pi halves. Cool. This is the cleanest, nicest, simplest answer that we can get here. I'll take the great answer. I'll even take the good answer. But I want you to be aware that these things can be presented in a few different ways. All right. So we have 2 more problems to get through, and we're at roughly the 30-minute mark. Let's just knock it out. The last 2 techniques that we're going to see, or the approaches to solving problems like these, come from something that we all love and care deeply about. An additional example here, we're going to do some factoring. Now, this has seemingly been, I don't want to necessarily say a weakness, but not our greatest strength throughout the year. So I would encourage, if need be, on the classroom, the factoring checklist or guidelines or flowchart, whatever we did, I believe it's still available on there. We need to make sure that we get solid with factoring. So here we go. We're going to jump right in, and I'm going to talk through one. And then I'll provide another one for you guys to talk through, but I have two more that I want to get through. I'm going to let you use your judgment as a class to make sure that we can see the entire video. Because if we don't finish it in class, that's fine, but you're going to be asked to watch the rest of it at home and then work the assignment. So here we go. I want us to solve the following. I want to know, when is it true that sine squared phi is equal to twice the sine of phi, or 2 sine phi, if you will. Now, as we're looking at this, it starts to feel a little bit uglier. I don't want you to physically write this, but I want you to be aware of it. In this situation, if we were to let some variable, I don't know, like x, for example, equal the sine of phi, then this would have the expression here in front of me. This instead would be x squared equals 2x. And if we were asked to solve that, it is much less intimidating. It's the exact same problem, minus one little trig step, but it's much less intimidating. I'm going to keep writing sine and cosine, or sine in this case, but I'm going to use this idea. So here we go. Anytime that we're solving something trig related, we are looking for the solution, the root, the zeros. So I want to make this equal to 0. And if ever possible, I'm going to keep my largest power, the square in this case, positive. So I'm going to subtract 2 sine phi from each side. So the next line then, we get sine squared phi minus 2 sine phi, and that's equal to 0. And now we're just running through the regular old factoring. I'm going to check all down my list, and I recognize immediately that, okay, they both have a sine phi. So let's factor that guy out. The sine of phi factors out, and it leaves behind a sine phi minus 2. Okay. Now, we are at a point where all we have to do now is apply ZPP, or the zero product property. I know that one of two things, or both, is true. It is either, and I'm going to change color just so we can differentiate between these. It is either that this first factor, sine phi, is equal to 0. I'm going to fix that phi. So either sine phi of equals 0, and I'm thinking about my unit circle, and I recognize that, oh, well, that happens at 0 and pi and 2 pi and 3 pi and 4 pi and 5 pi. So I'm just going to simplify that by saying, hey, pick any n as long as it's an integer and multiply it by pi, and we have it. This answer, or this factor, leads to this root. And I'm going to switch colors one more time. And let's see, I'm feeling green with envy because you guys get to do this. I get to do it too, but it worked for the color. The other factor, sine phi minus 2 equals 0. And again, I hate that phi. I don't know why it's coming out so ugly. And instead of saying sine phi minus 2 equals 0, I'm going to add 2 to each side immediately. Now, warning, warning, warning. Be really aware here. The largest value of sine that we ever get on the unit circle anywhere is what, Kalisha? Louder. Okay, yeah. When we look at the unit circle, the biggest sine ever gets is 1. I'm telling us that sine is equal to 2. This is never, never true, which means this solution that we would get from this factor is extraneous, and therefore it's garbage. We don't have it. There is no root based off of this factor. So the only solution that we have for this problem is n pi. And that's a weird statement because when I say the only problem, it's really all infinitely many solutions. Sorry, when I say the only solution, it's infinitely many of them, but it's from this one factor right here. Cool. Okay, rather than having you guys do this one in class, I would encourage, if need be, I want you to look at example 3 on page 366. They do something very similar where they go through factoring. Check out that example. There's another factoring example, which means we have saved just enough time to work our final problem for the first half of this section, where last named example, and I think this blue is going to show up, but we'll see. Last named example is our quadratic type equations. So we are going to be factoring still some more, but these are going to be quadratic type. And when I say quadratic type, all I mean is that for some trig function, instead of just x, but I'm going to use x in this, we can write a x squared plus bx plus c equals 0 and solve it just like we would regular factoring using our grouping, using our PQ lists conceivably, but we're not going to do that here. But there's only one or two little things that have to happen that we'll see extensions of this tomorrow with a shorter video. So the first example here that I would like us to solve, or that I would like to solve, is the following. I want to solve and determine when is the equation 2 cos squared x minus 5 cosine of x plus 2. When is that equal to 0? Now, to make things a little bit nicer, we are going to work on a closed interval or a specific interval. And the one that is natural for us to use is that first period where we say, I want to find answers from 0 to 2 pi, where I include 0, but I don't include 2 pi. Because if I did, we would get two solutions because 0 and 2 pi are the same angle. So closed on the left means I include it. Open on the right means I don't include it, but it really was because of the cyclic nature of these things. Now, just like I've been doing, I want to show the important easy connection to make these problems so much easier. If you really want to rewrite these, you can. I typically don't, but if we wanted, we could use a little substitution just to make it look nicer. If I let u equal cosine of x, then we could rewrite this expression much nicer. This could be 2u squared, because u is cosine of x and we squared it, minus 5u plus 2. And since I've already committed, I'm actually going to work this one with u, but again, I normally would not. So now it's just a matter of factoring this. So I'm going to run through the list of our factoring techniques that we have for quadratics to see if we can hit one. So first thing I check is a greatest common factor. I know that a 2 goes into 2 and 2, but it doesn't go into 5. They don't all have a u. There is no GCF other than 1, which means there's no meaningful greatest common factor. All right. Beyond that, the leading coefficient is not 1. This is a trinomial, so I didn't even bother to check difference of squares. It's a trinomial, and the leading coefficient is not 1. Since that leading coefficient isn't 1, it means we get to factor with grouping, where I take the leading coefficient and the constant, and I multiply them to get 4. And I now need two factors of 4 that add up to a negative 5. So easiest choice right off the bat is 1 and 4. But if we add these, they sum to positive 5. But we can fix that by making them both negative. So I'm going to change something just to highlight this. And all I've done is I change the colors to make sure that we can really see what's happening here. So remember, when we're grouping, all we're doing is taking a trinomial and we're rewriting it with 4 terms to make it a four-nomial, which I can split into two equal-sized groups. So I'm going to replace this negative 5u with a minus u. And then this always feels wonky, but we're going to add a negative 4u, and then we'll kick back over to plus 2. Now, I'm not going to switch my colors anymore, but I just want to really highlight this 5 is still here. We just split it up. And we split it up very intentionally so that we can recognize and do this lovely grouping technique, ensuring that we have our plus sign in between so we don't make multiplication happen where it didn't. And now we're just going to keep kicking. So here we go. Looking at this first group, I see I could take a u out of it, and it would leave behind a 2u minus 1. And over here, to give myself the exact same expression, I would need to factor out a negative 2, and it would once again leave behind a 2u minus 1. And that's still all equal to 0. So I see two factors. And I'm going to work up this way just in the interest of space. But my very next line, I see one factor has the form u minus 2, and the other factor is 2u minus 1. And their product is equal to 0. So because we've done this u substitution, the only concern that I have is somebody solving for u and just stopping there. Once we get here and we actually solve each of these factors or set each of these factors equal to 0, I would strongly recommend that instead of writing u minus 2 equals 0 or u equals 2 if we set it equal, so I would not write this every time, and I'm actually not going to write it now. I would switch it back. I know that this one is telling me the cosine of x minus 2 is equal to 0, and I know that this one is telling me 2 times the cosine of x minus 1 is equal to 0. Okay, here we go. We're looking good. This one, garbage. Never happens. And again, because Kalisha told us just a second ago that sine never gets bigger than 1, cosine also never gets bigger than 1. They're just different dimensions, or axes, if you will. This one has hope, though. We had an extraneous solution on the first, but let's try this. I will add 1 and divide by 2. And here it is. And now I'm looking for anywhere between 0 and 2 pi, or more simply put, 1 unit circle, no more than 1. Anywhere on there where cosine of x is equal to 1/2. And if you dig around on the unit circle for just a moment, you're going to find that this happens first at pi thirds. It does not happen at 2 pi thirds because cosine is negative there. It doesn't happen at 4 pi thirds in quadrant 3 because cosine is still negative. But in quadrant 4, we have it. 5 pi thirds should be the last. Now, I don't have a unit circle in front of me, so hopefully these are correct. If I'm off, that's my bad. I don't think I am. No, I feel okay with this. And we have it. Cool. Much like the previous one, if you would like another example, I will work one more. But for all intents and purposes, this video can be done for now. Cool. So I will continue here in the next video, and hopefully you guys get a little bit of time in class. The homework this evening can be found on this page right here like this. Now, this assignment looks large. We have only completed part 1 of 5.3. For this evening, if you would like to get as much of it done as you can, the only part of this that we have covered thus far is up through 34. So this is today's video. Tomorrow's video will pick up right here and we'll see a couple more techniques, but this is part 1, which we just covered, and this is part 2. Now this week, I know I mentioned it, I imagine that Ms. O'Malley also mentioned it with you guys, but the assignments this week in Google Classroom you will see, and I'll pull it up here for us. We'll see if this is Google Classroom. This is Google Classroom this week. So what I have indicated is that, hey, these examples, 5.2's assignment, or 5.3 rather, because that's the one we're doing. Much like the video yesterday, but I don't remember what I said because I recorded in the middle of the night. The entire assignment is due Friday at 11:59 p.m. and I want you to take a picture of it such that it can be read, and I want you to upload that picture to the assignment in Google Classroom. The picture of your work solving this. So at home, take a picture, email it to yourself, upload it to the assignment, and I can check it that way. As you look at it, I want all of this on Friday. So hopefully there's a little bit of time left. If there's not, I would encourage you to start working on it this evening. We can stop the video here. Anybody who wants maybe one additional example before we call this, you can either watch this at home, or if as a class you guys decide you want it, I'm going to work one additional problem right here that if you want it in your notes, this would be example B, and you guys can turn this off and it'll be available. It will be available at home if not everybody in the class wants it, or if nobody in the class wants it right now. So I'm going to go ahead and talk through this one. The video can stop here unless you want the additional example. So here we go. On B, if you want it, I want to know, when is it true that 2 sine squared x minus 3 sine x plus 1 is equal to 0? So this example, much like the other one, I noticed that if I let u equal sine x, I could rewrite this. Now, I'm going to run through and work this more in line with what I would typically do if I were just solving one. And I'm going to run through my list. There is no greatest common factor. It is not a binomial, so difference of squares doesn't need to get covered. It is a trinomial, but the leading coefficient is not 1, so it is not going to be a nice shortcut trinomial. So I will factor by grouping, where I'll multiply 2 and 1 to get a 2, and I recognize that -2 and -1 are the two numbers that multiply to be a positive 2, but add up or sum to the -3 right here. So I'm going to rewrite this entire expression where I will simply replace -3 sine x with this lovely -2, and I almost wrote x, -2 sine x plus a negative sine x. So there's my -3 total in that dark red color. And we'll go one step further and just say plus 1 still equals 0. Awesome. So we have it. It's just waiting to be solved at this point in time. I'm going to group this guy together, and I'll try to use consistent orange color, but I think I selected a different one. I'll group with my plus sign in between. I see a 2 sine x comes out here, leaving behind a sine x minus 1. To make the same factor spit out on the right side, or I don't want to say the right side because that implies the equal sign. In this second piece, I'm going to factor out a -1 to switch those around. So we get sine x minus 1. So these guys match, which is what I need, and this one matches this one, or matches with, rather. So I now see that my factors are 2 sine x minus 1 and sine x minus 1, and that's equal to 0. So I should have included it from the get-go. I didn't because I did it on the first one. I am going to solve this on the interval 0 to 2 pi. Cool. So this factor, to be 0, I would have to add a 1 and divide by 2. So I would obtain sine x, add a 1, and then divide by 2. So where is sine x 1/2 is this first piece. And while I can identify that, if I look around the unit circle, there's several places where sine x is positive 1/2. The first of these happens at pi 6ths in quadrant 1, and the second time happens at 5 pi 6ths in quadrant 2, because I'm looking at the y values for sine. From this one, it simplifies down. I'll add 1 to each side, and I'm just simply asked to find where is sine x equal to 1. And well, those, if I look at the unit circle and see where is y1, I see my first point happens at pi halves, and the second point happens at 3 pi halves. And we have found all 4 of these solutions. Cool. So hopefully, if anybody watched it, this extra video or extra example helped a little bit. If not, I enjoyed it, so that's all that really matters. Just playing. Cool. Good luck with the assignment. I would get started and up through number 34. Reminder, if you have issues with these and for some reason you're afraid to ask the wealth of knowledge that's, there in the classroom with you, between you and your peers, feel free to shoot me an email. I will try my best to address it either in an email response back or in a short little video reply if I get a bunch of the same questions. So I will see you guys in the next video, and later.